Hello and welcome to the first real mathematical, I don't even want to call it a lecture, but kind of just some cool stuff I want to talk about mathematically, and this is going to lead to a lot of things. So in my head, I kind of have an order I want to go through in these videos because I kind of want to give you an introduction to a few things that you're going to find useful later on, not only in the actuarial exams, but in calculus. So we're going to kind of back up because you really need to have a base in calculus, a base in counting, and a base in probability in order to even really start on some of the cool actuarial type stuff. So I'm going to do a variety of videos talking about these types of things, especially in calculus, and those will lead to actuarial type videos later on. So this video right here, I'm going to talk about two things called permutations and combinations. And I'm starting with this for a very specific reason because they're going to be used later on in some of the proofs that I'm going to show you and teach you about. And really it's going to be a base for some of the calculus theory that I'm going to teach you about. And I'm in a very simple way, I'm going to explain the basics of calculus to you. You should understand what a derivative is, what an integral is, and some other very basic type things of what really makes up calculus. That will come later on. So right now, I'm going to start with permutations and combinations. This is a way of counting. You know, a lot of people say, well, counting is not that difficult, right? It actually can be quite difficult. It's very easy for me to count the fingers on my hand. You know, 1, 2, 3, 4, 5. Very easy. That's one way of counting, right? What gets a little more complicated, and I have actually a box with a few things in it as an example. So what I have here, and it's probably kind of hard to see on the screen, so let me show you. I've just got these little magnets that pop on the clipboard. I've got 4 of them. So what we've got is a yellow, red, green, and blue magnet. We've got 4 of them. And what if I were to tell you that I'm going to put these magnets in a box? I've got 4 magnets, and I'm going to randomly draw out 2 magnets, right? So 1, 2. I pulled out a red and a green magnet. The question is, the first question that I'm going to answer is, how do I count the number of ways that I could pull out 2 magnets? I could pull out a blue and then a yellow. I could pull out a yellow and then a blue. I could pull out a red and then a yellow then a red. I could pull out a green and then a blue. There's a variety of ways I can do that. And how do I go about counting that? That's a little more complicated than counting the fingers on my hand. So in this case, of course, what I'm going to do is I'm going to say it does matter the order I pick them in. So I'm going to count, if I pick the yellow one and then the red one, I'm going to count that as one way of doing it. What if I pull the red and then the yellow? I'm going to count that as another way. So in this first example I'm going to give you, I'm going to say order matters, and that is something that we call a permutation. And then the second one, order will not matter, and we'll count those 2 examples as the same, and that's called a combination. So let's just start with, so kind of the title of my talk here is counting. And so let's just start with the first one here is permutations. And permutations is really asking exactly the question that I stated there. If I have a certain number of things, how many ways can I draw a subset of those things where order does matter? So what we're going to do is we're going to denote this with a P. This is how many texts do it. In, comma, K. What this means is out of in we're going to just say objects to simplify this. Out of n objects, how many ways can I pick k of them? And we're going to say order matters. What does order matters mean again? That means red, blue is different than blue than red. So the order in which I draw these items does matter. So think about this for a second. We've got 4 different objects. 1, 2, 3, 4. When I first have this box, and I've got my 4 magnets in here, my first choice, I have 4 possibilities for my first choice, right? So I'm going to show you this here, that I've got 4 choices. After I pick that first magnet out, in this case I chose red, it could have been any of the other colors, but in this case I chose red, how many do I have left? I have 3 left, right? So I'm going to put this red one, right here. Okay, so for my second choice, I have 3. Now, with these 2 numbers, we just multiply them, because right here, for the particular red one, right, if I put a red magnet here, I've got 3 different ones I could put here. I got green, I got yellow, and I've got blue. So there's 3 combinations right there. Well, what if I had chosen green to be my starting magnet? Then I got 3 more, right? So I got 4 cases here multiplied by 3, and my total is, there are 12 different ways for me to pick 2 magnets out of this box, where order matters. What's a simpler way where I don't have to think about all this every time? So I'm going to remind you or teach you about something called a factorial. If you don't know what it is, that's okay. Factorial is something where if we have, let's just say if we have 3 factorial. Factorial is denoted by an exclamation point. I know it's kind of weird. I don't know why, but it is. So 3 factorial is equal to 3 times 2 times 1. Likewise, 5 factorial is equal to 5 times 4 times 3 times 2 times 1. It's a way it's a simple way of showing multiplying all the integers down from that integer all the way down to 1. So think about, I just wanted to explain that real quick just to give you a background on factorials, but if we jump back up here to our permutation, what is another way of thinking about this? Because we want to generalize it for the case of n and k. In this case, where we were picking 2 out of 4 magnets, we were talking about the permutation of 4, 2, right? So in this case, n equals 4 and k equals 2 in the case of our magnets. But we want to generalize that for any n and k. So if you think about it here, all we really did was we took 4 factorial, which was, oh, let's just make some room here, which was 4 times 3 times 2 times 1 divided by 2 times 1. Because that cancels, and we're left with 4 times 3. So, really, because the reason I say this is because let's say I was doing the permutation of 7 choose 4. Well, I shouldn't say choose. That's used that's terminology for combinations, which we'll talk about in a little bit. I should say the permutation of 7 and 4. In that case, we would do you know, we would have seven different lines, kind of like this, and we would do 7 times 6 times 5 times 4, because we have 4 different magnets that we're choosing from a box of 7. I just keep using an example of magnets. But all we've done here is we've divided out the rest of that factorial. So a more general way of saying, this whiteboard is just way too small. But let's just pop up here. And a more general way of saying P in K, that's equal to n factorial divided by n minus k factorial. So in our example, when we just plug in the numbers, in our example of P42, that's equal to 4 factorial divided by 4 minus 2 factorial, which is equal to what? 4 times 3 times 2 times 1 divided by, sorry, that should go outside like that. 4 minus 2 is 2. 2 factorial is 2 times 1. Boom, it cancels out. Division cancels that out. We're left with 4 times 3, which is equal to 12 ways of picking out 2 magnets where the order matters. And I know I keep saying the order matters because that's an important distinction when counting. Because in this case we're saying if we draw out a red and then a blue, or a blue and then a red, we're counting those as 2 different cases. Yet sometimes you may want to count that as just 1, because really when I draw out the red and the blue, it is the same combination of magnets. When I hold them in my hand, it's the same 2 magnets. It's just I may draw them out in one order or another. So that's the basics of what a permutation is. You may or may not have heard of that. That was just kind of a simple example of how you would use something called a permutation. Okay, now let me get into a combination. Let's use the exact same example, but in this case, we want to count pulling out the 2 magnets, whether it's blue than red or red than blue. We want to count that as the same one. We don't want to count that multiple times. Where we're counting that case as 2 here. 2 of our 12 is that where the order matters. So let's talk about where order doesn't matter. Make some room here. Where order does not matter, we're talking about something called combinations. This is the other type of counting, and we're going to say order. I don't know why I'm writing in all caps. Does not matter. So if you think through this, let's just use the same example where we have our 4 magnets. We're going to think through this, and really the whole thing is the same except for the very end. So we've got our 1, 2, 3, 4. In the same way, when I first draw my magnet, I've got 4 choices. I've got red, blue, green, yellow. Boom, it could be any one of the 4. Then I'm left with 3. I've got 3 left, so 4 times 3, there's my 12 combinations. The problem is, like I said, when I draw the red first and the blue second, that gets counted as part of my 12. But what if I draw the blue first? That's one of my 4. And then I draw the red second. That gets counted as one of my 12. So we're going to start. We were very close to counting the correct amount. So we know we can at least start with, and we're going to denote the combination instead of, this is the permutation, P N K. So that's permutation. And then we're going to denote the other one, just because many texts do it this way, in K. They do it with a parenthesis in k in over k, and that's the combination. So that's the way we'll denote it. Well, we're going to start with the permutation formula because we're really close to what we want. So we're going to start with our n factorial divided by n minus k factorial. So really all we have to do, well in this case we have 2, right? So we got to think about how much are we double counting? How much do we want to divide back out to get to what we want? Every time I draw 2, we've got red then blue, and we got blue then red. I have 2 combinations. If it's yellow and green, we got both ways. So we've really double counted every single combination, just by an order of 2 in this case. So we really want to take our number, well, let's actually write that out. For this case, 4 factorial divided by 4 minus 2 factorial. We want to take this whole thing. Wow, that was a horrible parenthesis. I don't know what happened there. That was a bracket. And we want to divide by 2. And then we'll get to the number that I want, which in this case is going to be 12 divided by 2, which is 6. That's the number I want to count. But this gets a little more complex when you don't just have 2. So let's think about that for a second. Before I write a general formula for n choose k, that's the way you say this, by the way. For a combination, you say n choose k. In this case, it would be 4 choose 2. Okay, let's erase this, make some room here. Combinations order does not matter. Get rid of that for a second. Okay. So what we really want to think about is the generalized case, because 2 was a little bit easier in the sense that I could say to you red then blue, blue then red. We know there's 2 ways of ordering these things. The problem is, what if I'm doing something like 4 choose 3? Okay, so we got 1, 2, 3, 4 slots here, and I'm choosing, well, the first 3 is what I'm picking out of the box. In that case, how much am I overcounting? Well, let's just pull out the yellow one, and let's think about this for a second. Let me put these up here. Red, blue, yellow. If I'm choosing 3, how many times have I counted this particular combination? When I'm doing a permutation, I'm counting that. Then let's flop the yellow and the blue. I'm counting that. There's 2. Okay, let's start with the yellow. There's 3. Now let's flop the red and the blue, or the red and the blue. There's 4. And then the last one, if we start with what did I start with? I can't even remember now. Did I start with the red the first time or the blue? I think it was the red. I'm going to have to rewatch this video to see, but okay, let's just pretend it's blue. So we start with the blue, then we got yellow, red, red, yellow. There's 2 more, so there's 6. There were 6 total times that I counted this when I really only wanted to count it once. So how do I get 6? How do I get 6 down to 1? I divide by 6, right? To get down to 1. In the case of the 2, when I had 2, how do you get 2 down to 1? You divide by 2, which is what I did. I divided my 12 by 2, so I counted each of those combinations 1 time. Each of those 6 combinations got counted twice, which is how it got to 12 in the permutation, but I got it down to 6 with a combination. When I'm choosing more than 2, I got to think about all the ways to order these things. So, well, how many ways are there to order these 3? You can think about it in the same way we were kind of thinking about a permutation. When you have 3 things, you got 3 times 2 times 1. What is that? That's 3 factorial. When I have 4 things, I have my first one, which I have 4 choices. So let's go up here. Say I have 4 objects, 1, 2, 3, 4, and I'm just counting the ways to order those objects. I have 4 total objects for my first, when I draw up my first magnet. I have 3 for my next magnet, then I got 2 left, and then I got 1 left, which is just 4 factorial. Okay, so let's back up for a second. In the case of 4 choose 3, when I have 4 total magnets and I'm choosing 3 out of the box, all I have to do is take my permutation formula, which is P43, which we talked about earlier, and divide it by 3 factorial. In the case of 4 choose 2, I divide by 2 factorial. In the case of 7 choose 6, I would divide by 6 factorial. Because we're just counting the ways that we can order these things, and we're dividing out our extra counting. How much do we extra count it for the order? Okay, so that's cool, which means we can really just generalize this. So if we back up here. So basically what I told you is I said if we have n objects and we're choosing k, and we're saying order doesn't matter, we just have to think about a permutation formula to start off, which is P in K, and all I'm doing is dividing by K factorial. Alright, so let's simplify that a little bit because we don't know what P in K is, so let's just, well, we do know what it is, but let's kind of combine all this stuff. So we talked about P and K. What was P and K? That was our permutation, which was equal to, we derived it on the last one, was n factorial divided by n minus k factorial. Right? That's the permutation piece right up there. And now we're going to divide that out by k factorial. Okay, so let's make some room. Let's get rid of our magnets here. Put these down. Finally, just to make things simpler, when you're dividing you have a fraction, dividing that, you combine the denominators, so that's the same as n factorial divided by k factorial times n minus k factorial. So there's our final formula for a combination. We've derived n choose k where order does not matter. Let's just test it real quick. Let's test it on our 4 choose 2, because we said 4 choose 2 should equal 6, right? We said if we were talking about order matters, which is a permutation, P4, 2 was equal to 12. Then we said, okay, we want order to not matter, and we derived 6 because we said we were double counting each of those. So let's see if it works. Let's see if it works for 4 choose 2. Okay, let's plug in our n. So we got 4 factorial, n is equal to 4 in this case, k is equal to 2 in this case. Let's divide that out. We got k, so 2 factorial, n, which is 4, minus k, which is 2 factorial. Alright, so let's simplify that even more. We got 4 factorial divided by 2 factorial. 4 minus 2 is 2, which is 2 factorial. Alright, what's 4 factorial? That's 4 times 3 times 2 times 1, 24. 2 factorial is 2 times 1, so that's 2. So this is 2 times 2. What's 2 times 2? That's 4. 24 divided by 4 is 6. That was a weird circle. That's exactly what we wanted. We wanted 6 in this case. So boom, there you have it. That is 2 of the base ways that we count things, and counting can get very complicated, so we needed those formulas. And there are so many things that you can use counting for, and it's a base for probability, because probability starts with counting things. Statistics starts with counting things. So this is really kind of our base for that. And we will use this going forward. I'm going to use it in a few proofs going forward, and that's why I wanted to start with this, because I wanted this as our base so you knew what I was talking about when I move on to some other cool stuff. I'm going to do some calculus stuff, I'm going to prove a couple cool things, and then we'll dive into some actuarial stuff later. But this, if you understand this, it's a really, really great start. So thanks for joining me in this episode of Counting with Paul Johnson. And on that note, I will see you next time.